Hi folks, we're going to take a look at number 8 from page 418, and there's a bit of debate as to what they even mean by this question. So let's take a look at it. It says the diagonals of a parallelogram are determined by the vectors x and y. So the way I read this is that these vectors here represent the actual diagonals. Okay, but I suppose one could think are determined by these vectors, meaning those are your two side lengths, and then they determine two diagonals, which seems a little odd because the diagonals then would have nothing to do with the question, and it's just simple. You just take the cross product of these vectors, the magnitude, and that gives you the area of the parallelogram. So not an interesting question, and certainly not well phrased. So what I'm going to do is I'm going to take the perspective that these two vectors actually represent the diagonals of the parallelogram as opposed to the sides of the parallelogram. Okay, it's a much more interesting question, and forces us to think a little bit. Okay, so let's take a look at what we have. These two vectors here are going to represent the diagonals. So if I draw a picture to represent this, okay, so if I don't know what the sides are, I'll call them vectors A and B. Okay, and of course these determine parallelogram. And so we know that one of these vectors is going to represent one diagonal, which would represent the sum. So say this is A plus B, and the other diagonal is going to represent the difference, say A minus B. So I guess the question is well, how do we know which one represents the, which diagonal? Okay, well, if you think of it this way, what if I were to take another configuration? Let's say I were to put A and B like this here. Okay, I realize that this vector is going to be the same length as this vector here, which in my first diagram is the sum of the two vectors. In the second diagram, it's the difference of the two vectors. And if I look at the other diagonal, this one here, okay, in this configuration, this length is just the magnitude of the subtraction, whereas in this configuration, this length is just the magnitude of the sum. So in the end, it doesn't matter which one we call the sum or the difference. It's going to generate the same area parallelogram. Okay, so I'll use this diagram to help me out. So let's say I let x be equal to the sum of A plus B. Okay, and so that means y is going to be equal to the difference of A and B. Okay, but what I need in order to find the area of this parallelogram are A and B themselves. I need the side lengths, which then I can take the cross product of, and the magnitude to find the area. So this is where we have to do a little bit of algebra. So can I combine these two vectors to get A? And then we realize, oh, wait a minute, if I add x and y, okay, so if I take x plus y, okay, what do I get? I get A plus B plus A minus B. And we see that the B vectors just cancel out to give us a 0 vector, so I'm just left with 2 times A. Okay. So if I just want the vector A, I just divide both sides by 2. Okay. So that means that the vector A is just given by x plus y divided by 2. Okay, so let's find that. So x plus y, so 3 plus negative 1, so that's 2 divided by 2 is 1. Negative 3 plus 7 is 4, divided by 2 is 2. And here 5 plus 5 is 10, divided by 2 is 5. And now what I have is I have the actual vector A. Okay, so hopefully you can see I can do something similar to find the vector B. Is if I subtract these two, well, let's see what happens. Vector x minus vector y, so A plus B minus A minus B. Well, here the A vectors cancel out, and I'm just left with B minus negative B. I'm just left with 2B. Oops, x minus y. Okay, and so here if I want the vector B, I just divide by 2. So the vector B is just given by the subtraction divided by 2. So let's do x minus y. 3 minus negative 1 is 4, divided by 2 is 2. Here, negative 3 minus 7 is negative 10, divided by 2 is negative 5. And here we have 5 minus 5 is 0, divided by 2, of course, is just 0. Okay, and so now that I have vectors for the sides of this parallelogram, I can now use the cross product to find the area. Okay, so the area is just going to be equal to the magnitude of A cross B. Okay, let's find that out here. So here, if I have 1, 2, 5 with the extra 1 there, and then 2, negative 5, 0, the extra 2 on the end, let's calculate A cross B. Okay, so the x component will be 0 minus negative 25, so just 25. Here we have 10 minus 0, so just 10. And here we have negative 5 minus 4 is negative 9. Okay, and so here that's just going to be the square root of 25 squared plus 10 squared plus negative 9 squared. So let's get the calculator to estimate that. And what do we have? Square root, oops, wrong one. Square root of 25 squared plus 10 squared plus 9 squared and 28.4, about 28.4 units squared since it's area. Okay. Now, just something interesting. You sort of, if you look at the answer in the back of the book where they assume that these vectors were the sides of the parallelogram, you'll notice that it's exactly twice this number. Okay, and in fact, you can prove with a little bit of algebra, nothing too difficult, you can actually prove that if you take the cross product of the diagonals, you'll get twice the area of the parallelogram. Okay, but since it's not something we established, we can't use that. We needed to go through the process of finding that. Okay, so again, just to recap here, if we take these vectors as representing the diagonals, you just have to remember that the diagonals have a physical significance. One diagonal represents the sum of the two vectors that represent the sides, and the other one the difference. And from there, we were just able to use some slightly clever algebra to determine those two sides. Side vectors, and then use the cross product to determine the area. Okay, that's it for this one.